Assalamualaikum and salam sejahtera everyone. For today's lecture, we will move to the last part of chapter 6. These are the learning outcomes of this chapter. At the end of this chapter, I hope that you are now mastering in generating and interpreting the root table in order to determine the stability of the closed-loop system. This week is the last week of lecture for this semester, and we will cover the last part, which is part 3 of chapter 6 today. For this week's lecture, we will continue with Root-Hewis criterion for stability. We will take a look at some examples of standard Root-Hewis, two special cases of Root-Hewis, and designing Root-Hewis for stability. Let us demonstrate the usefulness of the Root-Hewis criterion with a few additional examples. 5. Find the number of poles in the left half plane, right half plane, and on the imaginary axis for the system of figure 6.3. I will always keep asking this question. What is the first steps to be taken in solving this example? What is the first steps to be taken in solving this example? Yes, finding its closed-loop transfer function. How? I hope you know how to obtain the closed-loop transfer function for the system in figure 6.3. Then, my second question is, why finding the closed-loop transfer function? Why finding its closed-loop transfer function? Yes, you are absolutely right. We are looking for the closed-loop transfer function because we want to find its closed-loop denominator equation. Now, we already have the closed-loop transfer function for the system in figure 6.3. And we only interested on the denominator of the system. You may now start creating the root table. Table 6.9 is the completed root table for example 5. As seen in the table, there are no special cases occur in the table. There is no zero in the first column of a row, and there is no row with entire zero values. Therefore, we do not need to find epsilons and a polynomial for this exercise. Then, we can proceed with interpreting the table. Based on the first column of the table, there are two sign changes occur from s power of 2 to s power of 1, and from s power of 1 to s power of 0. Therefore, the system has two right half plane poles. The remaining two poles are at the left half plane pole. The system cannot have j omega or imaginary pole since a row of zeros did not appear in the root table. The system has 4 poles since the highest power of denominator of the transfer function is s power of 4. Example 6. Find the number of poles in the left half plane, right half plane, and on the imaginary axis for the system in figure 6.4. This example demonstrates the occurrence of a zero in the first column of a row. So, how to solve for this example? Yes, finding its closed-loop transfer function using equivalent feedback formula. Table 6.10 is root table for the system in figure 6.4. From the table, we can see that a 0 appears in the first column of the S power of 3 row. In order to form the next row, which is S power of 2, a division by 0 is required. Since the entire row is not 0, simply replace the 0 with epsilon and continue to complete the table as usual. We now have the completed root table for example 6 using epsilon value. Since the stability of the closed-loop system using Routh-Lewis criterion is determined based on the first column of the root table only, therefore our attention will be only on the first column of the root table. Therefore, the second and the third column can just be ignored. Permitting epsilons to be small positive quantity, let's say positive 1. Replacing epsilons with plus 1 value give the term in S power of 3 row to be plus 1, S power of 2 row to be minus 1, and S power of 1 row to be plus 2.33. Thus, there are two sign changes from S power of 3 row to S power of 2 row and from S power of 2 row to S power of 1 row, and the system is unstable with two poles in the right half plane. The remaining poles are in the left half plane. You may also replacing the epsilon with a small negative quantity, let's say minus 1. Replacing epsilons with minus 1 give the term in the S power of 3 row to be minus 1, S power of 2 row to be plus 7, and S power of 1 to be plus 1.48. Thus, there are two sign changes from S power of 4 row to S power of 3 row and from S power of 3 row to S power of 2 row. The system is also unstable with two poles in the right half plane. The remaining poles are in the left half plane. Example 7. Find the number of poles in the left half plane, right half plane, and on the imaginary axis for the system of figure 6.5. Draw the conclusions about the stability of the closed-loop system. The first step that should be taken in order to solve this example is to find its closed-loop transfer function using the equivalent feedback system formula. The closed-loop transfer function for the system of figure 6.5 is Ts equal to 128 over S power of 8 plus 3S power of 7 plus 10S power of 6 plus 24S power of 5 plus 48s power of 4 plus 96s power of 3 plus 128s power of 2 plus 192s plus 128. Using the denominator, form the root table as table 6.11. A row of 0 appears in the s power of 5 row. Thus, the closed-loop transfer function denominator must have an even polynomial as a factor. Written to the s power of 6 row, form the even polynomial. The even polynomial based on s power of 6 row is ps equal to s power of 6 plus 8s power of 4 plus 32s power of 2 plus 64. And its differential equation that will replace the row of 0 is equal to 6s power of 5 plus 32s power of 3 plus 64s plus 0. Then completing the table until s power of 0. As seen in the first column of the table, there are two sign changes occur in the first column. As seen in the table, there are two sign changes occur from the even polynomial s power of 6 row down to s power of 0 row. Hence, the even polynomial has two right half plane poles. Because of the symmetry about the origin, the even polynomial must have an equal number of left half plane poles. Therefore, the even polynomial has two left half plane poles. Since the even polynomial is of 6th order, the remaining two poles must be on the imaginary axis. There are no sign changes from the beginning of the table, which is s power of 8 row to s power of 6 row. Therefore, the rest of the polynomial has no right half plane pole. The results are summarized in table 6.12. The system has two poles in the right half plane pole. The system has 4 poles in the left half plane, and the system has 2 poles on the imaginary axis. Therefore, the closed-loop system for example 7 is unstable because of the right half plane pole. Example 8. Find the range of gain K for the system of figure 6.6 that will cause the system to be stable, unstable, and marginally stable. Assume K larger than 0. This example demonstrates how the gain variations can move pole from the stable region of the S-plane onto the imaginary axis and then into the right half plane. The first step for this example is to find its closed-loop transfer function using the equivalent feedback system formula. The closed-loop transfer function of the system in figure 6.6 is Ts equal to k over s power of 3 plus 18 s power of 2 plus 77s plus k. The next step is forming the root table as table 6.13. The entry for table 6.13 can be positive, 0 or negative depending upon the value of k. If k is chosen to be less than 138.6, all terms in the first column of table 6.13 will be positive. Therefore, there are no sign changes occur in the first column of the table. The system is said to be stable and have 3 poles in the left half plane. If k is chosen to be greater than 138.6, the s power of one term in the first column is negative. Therefore, there are 2 sign changes occur in the first column of the table. The system is said to be unstable and have 2 poles in the right half plane and 1 pole in the left half plane. If k is chosen to be equal to 138.6, we will have an entire row of 0, which could signify imaginary pole. Returning to s power of 2 row and replacing k with 138.6, we form the even polynomial. Differentiating Ps with respect to s gives this differential equation. Thus, the differential equation has the coefficient 36 and 0. Replacing the row of 0 with the coefficient of the differential equation, which is 36 and 0, we obtain the root table shown in table 6.14. For the case of k equal to 138.6, since there are no sign changes from the even polynomial down to bottom of the table, the even polynomial has its 2 roots on the imaginary axis. And since there are no sign changes above the even polynomial, the remaining root is in the left half plane. Therefore, for the system of figure 6.6, if k equal to 138.6, the system is marginally stable. Try to do this exercise by your own. The answer is as provided below. You may compare your answer with my answer. That's all for this week lecture. I hope you enjoy my lecture. All the best for your exam and see you soon, inshallah. Assalamualaikum and bye.